In the quest to unravel the mysteries of the universe, there are certain concepts that we consider as universal laws, and at the top of that list is gravity. It is a concept so unshakable and widely understood that we often compare other such facts to it. However, do we truly understand gravity down to the smallest detail? Or is gravity a misshapen piece of a larger, more mysterious puzzle? One of the most fascinating discoveries in astronomy was made by French astronomer Charles Messier, who unknowingly discovered galaxies. Since then, galaxies have been the subject of endless fascination and study, and along with them, dark matter. Despite being such a popular buzzword, there is still little known about dark matter. While dark matter is the current standard model of cosmology, there are boundless mysteries surrounding the supposed elemental particle. Along with these mysteries comes our current understanding of gravity, which doesn't necessarily support dark matter. So, which is it? Do we not really understand dark matter or gravity? Or could it be that we have a flawed theory of both? In 1933, Swiss astronomer Fritz Zwiki stumbled upon something concerning during his study of galaxy clusters. While observing these clusters, Zwiki noted that the total mass of matter didn't account for the total mass he calculated based on the motion the galaxies held together by gravitational force. Either he had discovered that gravity was broken, or he had stumbled upon something else. Without any reason to doubt a law as unshakable as gravity, his calculations led to the proposal of a new type of matter that was unseen. Zwiki closely studied the Coma galaxy cluster, where he calculated its mass by observing the galaxies at the cluster's edge. He then carefully drew up the mass of the Coma galaxy using its brightness and the number of galaxies it contained. When he had finished, he had a true puzzle on his hands. While the two values should have matched to the very decimal point, they weren't even close. Despite perfect calculation and repeated study, Zwiki could never get the two values of mass to match. The only option available to him was matter he couldn't see. Thus, the concept of dark matter was born. No matter his brilliance, such a concept couldn't be held up by one man's research. The search for dark matter continues to this day, and we may yet unlock the secrets of this mysterious force that holds the universe together. Vera Rubin, a pioneering astronomer, joined the Department of Terrestrial Magnetism at the Carnegie Institution of Washington in 1965. Her mission was to analyze galaxy rotation curves to avoid the controversial areas of astronomy such as quasars and galactic motion. Rubin observed the orbital speed of visible stars and gases in a galaxy compared to the radial distance from the center, creating a graph that would lead her to discover something profound. Contrary to the observed behavior of planets in our solar system, Rubin found that the stars in the galaxy she studied behaved differently. To her astonishment, the outer regions of the galaxies rotated at the same or increased speeds of the inner regions, even though visible matter was distributed differently. This was impossible and brought Zwiki's theory of unseen matter into the spotlight. Multiple studies and observations supported the existence of dark matter, and it was further validated in the 1980s with the observation of gravitational lenses of background objects of galaxy clusters, and in the 1990s with measurements of cosmic microwave background and large-scale structure formation of the universe. Dark matter has become one of the most important structures in cosmology and astronomy, accounting for 27% of the observable universe. The problem with this unseeable matter, however, is finding it. The search for dark matter is a formidable challenge, as it is invisible and doesn't interact with electromagnetic radiation. The only way we can detect its presence is through its gravitational effects on visible matter. Despite our confidence that dark matter exists, particle physics currently lacks an elementary particle representation for it, and theories are still being developed to understand it. In this ongoing hunt for dark matter, there are several promising models that have emerged, such as WIMPs, axions, MACHOs, and sterile neutrinos. Scientists are conducting cutting-edge experiments to detect dark matter particles, including the use of the Large Hadron Collider and experiments such as the supercryogenic rare event search and the axion dark matter experiment. However, while these experiments are providing new data, they have yet to yield concrete results. It's possible that dark matter is simply too elusive, or it may not exist at all. But if dark matter doesn't exist, then how do we explain the phenomena observed by scientists such as Zwiki and Rubin? While the lambda-cold dark matter model remains the current accepted theory, other models such as aqua and modified Newtonian dynamics offer intriguing possibilities to explain the phenomena observed in our universe. Scientists and researchers continue to push the boundaries of our understanding with cutting-edge experiments and groundbreaking discoveries. As we uncover more about the nature of the universe, the quest to unravel the mysteries of dark matter and its alternatives will undoubtedly continue.